Good morning, distinguished presenters, specially invited guests, participants joining us from across Jamaica and overseas, colleagues, ladies and gentlemen, welcome. On behalf of the Bureau of Standards Jamaica, an agency of the Ministry of Industry, Investment and Commerce Jamaica's Business Ministry, and particularly on behalf of the Communication and Customer Service Branch of the BSJ, I warmly welcome you to today's online awareness session. Our session, Time Matters, Understanding Jamaica's Standard Time and its impact on business and daily life. Today's session is being staged in commemoration of World Meteorology Day, and that is celebrated annually on May 20. It's recognized internationally as an opportunity to highlight the importance of measurement science in our everyday lives. Now, when many people think of measurement, they often think about weight, temperature, length, volume. However, one of the most critical measurements in modern society, whether we know it or not, is time. Time influences virtually every aspect of our daily existence, from telecommunication networks, internet connectivity, to banking systems, transportation, broadcasting, GPS navigation, scientific research, manufacturing operations, and even the alarms that wake us each morning on our mobile devices all depend on accurate and synchronized time systems. Now, when we live in an interconnected and highly digital environment as we live today in 2026, even tiny inaccuracies in timing can lead to major disruptions affecting communication systems, cybersecurity, financial transactions, logistics, and operational efficiency. This webinar today seeks to increase awareness of the importance of accurate and synchronized time systems in society and deepen public understanding of how Jamaica's official time is maintained and disseminated through the Bureau of Standards Jamaica. We hope that all of us together will gain insight into Jamaica's national time standard system, the maintenance and dissemination of Jamaica's official time. And when we talk about Jamaica's official time, it is not Mesocom Jamaica time, which is 30 minutes or 60 minutes after the scheduled time. Jamaica's standard time is standard time. So we hope to also gain insights into the importance of synchronized systems for organizations, best practices for time management in the digital environment, and we all know how important that is. And finally, we will speak to you about the services provided by the Bureau of Standards Jamaica's Time and Frequency Laboratory. It is therefore my pleasure, on behalf of the entire organization, to welcome you and to thank you for joining us in this discussion. Let me just share some guidelines to help us
I'm
have
going
a
to forward it to you.
smooth
I'm going to forward it to you.
Let me just share some guidelines to help us have a smooth and productive session. We're going to invite persons to kindly keep your microphones muted throughout the presentations to minimize background noise and disruptions. I think that came in on cue. Participants are encouraged to submit questions using the chat feature during the presentations. Now, the specialists are the ones presenting, and they are the ones who will need to answer. So do exercise some patience as we give them time to get to the questions. If you wish to verbally ask a question during the question and answer session, please use the raise hand feature, and we will acknowledge you accordingly. We have reserved approximately 20-25 minutes at the end of the presentations for question and answers, and at that time, Our presenters, Terence Jones and Andrew Novick, will be available to respond to your questions. And we also encourage participants to complete the evaluation form, which we will share at the end of the webinar and which we will also share via email. Your feedback is very important to us, and it does assist us in improving future engagements. Thank you for your time and for your cooperation. Welcome to the Bureau of Standards Jamaica's World Metrology Day online awareness session, engaging in time matters. At this point, we're going to invite Kimo to play a video, The History of Keeping Time. So Kimo, if you'll just go right ahead and play that for us.
Ever wonder, where did telling time come from? Why does it matter what time it is? Who determined the clock, and why in the world are there so many different time zones? The first form of telling time was the sundial, and the earliest sundials known from the archaeological record are obelisks from nearly 5,000 years ago. Sundials indicate the time by casting a shadow onto a surface. The object that casts the shadow is a stick in the center known as a gnomon. A well-constructed sundial can measure time with remarkable accuracy, and sundials were used to monitor the performance of clocks until the modern era. But sundials have their limitations too. Obviously, they require the sun to shine, so they don't work at all during the night when it's dark. Many different devices have been used over the years to estimate the passage of time. Candles and sticks of incense that burn down at fairly predictable speeds have been used, along with the hourglass. Hourglasses are devices in which fine sand pours through a tiny hole at a constant rate and indicates a predetermined passage of an arbitrary period of time. The origin of the hourglass is uncertain, although beginning in the 14th century, the hourglass was used commonly, especially on board ships. The motion of the boat on the water did not affect the hourglass, unlike other time-measuring devices. The mechanical clock was invented in the 13th century, which sparked a big change in traditional timekeeping methods. This modern clock relied on the swing of a pendulum or the vibration of a quartz crystal, which was far more accurate than sand or candles. Today, the basis for scientific time is a continuous count of seconds based on atomic clocks all around the world known as the International Atomic Time. Why does it matter that we keep track of time? Well, time regulates our daily lives and makes it possible to accurately communicate with people all over the world. Without a time system, we would have many challenges in farming, social structures, communication, and business. Take the American railroad system, for example. In the mid-19th century, each railroad used its own standard time, generally based on the local time of its headquarters, and the railroad's train schedules were published using its own time. Some major railroad junctions served by several different railroads had a separate clock for each railroad, each showing a different time. The difference between New York and Boston is about 2 degrees or 8 minutes, which can be the difference between making or missing your train connection. If the difference between New York and Boston is 8 minutes, imagine the difference between Boston and Australia. The use of time zones irons out these differences and makes communication significantly smoother. A time zone is a region on Earth that has a uniform standard time. There are 40 time zones on land. Because the earliest and latest time zones are 26 hours apart, any given calendar date exists at some point on the globe for 50 hours. So the next time someone asks you, "What time is it?" your answer may be a whole lot more complicated than it used to be.
Thank you for that insightful presentation on the evolution of timekeeping. Indeed, the development of accurate time measurement has shaped civilization, science, navigation, communication, commerce, and technological advancement across centuries. We are seeing where we have evolved from the dial, the sundial, to what we have now. Today, precise timekeeping remains just as essential, perhaps even more so in a world driven by digital systems and global connectivity. Ladies and gentlemen, on this World Metrology Day, when we are speaking about the importance of trust, it is my distinct pleasure to introduce our presenters for today's session. Terence Jones serves as a senior metrologist in the Time and Frequency Laboratory here at the Bureau of Standards Jamaica and currently acts as manager of the Electrical and Electronics. He's a dedicated researcher and a technical leader who holds a Bachelor of Engineering degree in Electrical Engineering from the University of Technology, Jamaica, and is currently pursuing a Master of Philosophy in Electrical Power Engineering at the University of the West Indies, Mona. His expertise has earned international recognition, and we are very happy to have him here present today. He is a distinguished two-time recipient of the prestigious URSI's Young Scientist Award, having been honored both in 2024 and 2026. And joining him is Andrew Novick. Andrew Novick has worked in the Time and Frequency Division of the NIST, commonly since 1998. He is an electrical engineer with extensive experience in electronics for atomic clocks and measurement systems. Among his responsibilities, he manages and maintains UTC for NIST remote clock and oscillator calibration services and supports comparisons involving low Earth orbit satellite timing and a network time protocol, also known as NTP. Now, all of this, I'm sure we'll learn much more about today. Mr. Novick also created and operates the National Web Clock and serves as quality manager for the Time and Frequency Division at NIST in the United States of America. Andrew has co-authored more than 40 papers related to time and frequency metrology. Wow. Andrew certainly has had a lot of time on his hands. Today, both the gentlemen will present on the topic, why does time matter? Ladies and gentlemen, please join me in warmly welcoming Terence Jones and Andrew Novick. And we can put some emojis in the chat and make them feel welcome.
Good morning, everyone. Good morning. Just looking for some confirmation that my screen is being shared. Any feedback?
Yes.
Yep.
All right, excellent. Let me pull up one more file here. Yes, good morning again, everyone. I am incredibly excited that I've finally been given the opportunity to go on and on and on about the Time and Frequency Lab at the Bureau of Standards Jamaica. Before I get into the presentation, I just want to say that this is going to be somewhat of an interactive session, so I will do my absolute best to pay attention to the chat. Please go ahead and ask your questions for points that you aren't clear on. I definitely like the validation that what I'm trying to communicate is being effectively received. Before also getting into the presentation, I know Mr. Leng just gave an introduction to Mr. Andrew Novick from NIST, but especially I want to say that when the Bureau of Standards Time and Frequency Lab was being developed, I had to receive some specialized training in figuring out some of the problems that the lab was facing. And as such, I got the opportunity to travel to the National Institute of Standards and Technology in Boulder, Colorado, where Mr. Novick was my sponsor, my mentor, and trainer. He has helped the BSJ's team in a lot on our quest to redevelop our lab. And in doing so, he's also co-authored. Remember in the introduction that he has over 40 scientific papers that he has published. Mr. Novick has also co-authored 4 of the BSJ's research papers that have been published. I'm very pleased that we've been given the opportunity to make use of his expertise and to basically co-author this session with Mr. Novick. And let me say straight up that people, we are going to be getting the information directly from a man with great experience. There's very little out there with Mr. Novick's experience in time monitoring and time dissemination. Thank you again, Mr. Andrew Novick, for agreeing to have this webinar session with me. So getting into the presentation, I want to ask some questions to basically get the mind going, right? Have you ever checked the time on more than one devices and seen 2 different times? And how do we know which one of these times should we trust? How do we know which one of these times is the correct time? Where do you get your time from? And where you get your time from come from? These are some questions that I'm throwing out to the group. I'm going to be checking the chat to get somewhat of a response. Again, I want this to be a collaborative session. So if anyone is available and has been listening directly, you could just post in the chat. Where is it that you get your time from and why is it that you trust it? Before I move on, I'm dedicating a solid 30 seconds to a minute to this. Mr. Gale says he lean on the network service provider's time, right? Right, that is a very key one. Ms. James Noel says that she gets her time from the phone. Ronaldo says that he gets his time from the phone and the watch, right? And Larry Jones, my brother, said that he gets his time from Google. But why is it that we trust these sources? And who says that we're supposed to? Mr. Novick says that he gets his time from the sun. Why is it that we trust these sources? Why is these sources true? Why are they? Who tells us that these time sources are accurate? Let me put my chat over here. Who tells us that these time sources are accurate? Right? Another question that I want to pose to the group before I move on is, how do we believe that the second is defined? All right, what is your definition for the second? I'm going to be checking the chat as well. Miss Sonia Morgan says that she gets her time from the watch, the phone, and time signals. But about the definition of the second, Miss Morgan, how do you define the second? James Noel says that she defines the second as 1/160th of a minute. I have never thought of defining the second from Marsha Denny. Never thought of defining the second. So how is it that we know that 1 second is 60 seconds? One minute is 60 seconds, or 1 second is just 1/60. How is it that we know, right? So it is scientists like myself and more experienced scientists like Mr. Novick that operate time and frequency laboratories who maintains the definition, the official accepted definition of the second, right? So every country is supposed to have basically have a Bureau of Standards, right? And for Jamaica, Bureau of Standards Jamaica is the National Metrology Institute. And we talk about metrology. For those who online who aren't scientists, let me just first say that metrology is the science of measurement. If you pay attention to my little cartoon here, I cannot tell you if it is going to rain tomorrow, I cannot tell you if it is currently snowing in Boulder, Colorado, where Mr. Novick is. So the Bureau of Standards, being the National Metrology Institute for Jamaica, its key responsibility is ensuring that Jamaica's measurement system is internationally recognized. The purpose of the Bureau is basically to facilitate trade, right? We need to ensure that when we are doing any kind of trade, locally or internationally, what we define when it comes to measurement is what is true, is what is accurate, and it goes for that same definition internationally. So we need to ensure that when I go to the gas pump and I want to order, when I want to purchase 1 liter of gas, how is it that I know that I'm actually getting 1 liter of gas? Or when I purchase a kilogram of flour, or even the standard of the flour. If I want to manufacture sugar, if the Jamaica country, we manufacture sugar locally, and we want to trade our sugar for, let's say, flour from Mexico, there has to be an accepted standard, right? An accepted standard that makes it ideal for the trade of my sugar and accepting the flour from Mexico. So there has to be an organization, which is the Bureau of Standards, which ensures that each measurement that we're taking, that we're observing, remains true wherever we go at any given point in time. So we ensure that measurement traceability of the primary standards meet the internationally accepted standard. So what are the primary standard we might want to think of, right? What is the primary standard? So scientists online again would be familiar with the SI units as recognized by the International Bureau of Weights and Measures. I will further define what the BIPM is. So the SI units, we're familiar with the mole, the kilogram, the candela, the ampere, the Kelvin, the meter, and the second. At the Bureau of Standards, we maintain a specific standard for the kilogram, the ampere, the Kelvin, the meter, and the Time and Frequency Lab is in charge of maintaining the definition locally, the locally realized definition for the second. And this is the fundamental basic, people, for telling time, right? Was there a new definition given? I see Ms. Morgan says that 1/60th of a minute. Practically, but moons ago, I learned it was over 9 mil of something to do with oscillations with cesium electrons. Very foggy on the precise statement, right? You're somewhere in the ballpark, but I'm going to get further now into what it takes to actually define the second. So again, the core function of the Time and Frequency Laboratory is to operate we operate highly precise clocks, right? And maintaining Jamaica's realized time to the internationally accepted standard, which is Coordinated Universal Time. For those who aren't directly familiar with Coordinated Universal Time, or let me say for the old timers that are online, we might be familiar with Greenwich Meridian Time, right? And there's the prime meridian that runs through Greenwich in England. And it is from this we wanted to establish time zones and again get a general ensemble of what the time is. So Time and Frequency Laboratories across the globe, basically. It is their responsibility to maintain the official time locally and distribute that time with respect to their position. So the International Bureau of Weights and Measures, which is located in Sèvres, France, creates an ensemble, right, of basically the data that they are collecting from these time and frequency laboratories across the globe, and they create then Greenwich Meridian Time, which is now transformed into Coordinated Universal Time. So when we see the tagline UTC, we know that this is the officially recognized accepted time standard, and it is each country's time and frequency laboratory that supports, right, the generation of UTC, basically. So on to the definition of the second, right? Ms. Morgan was basically on point, somewhat in the ballpark of being on point, I should say, defining the second. So again, according to the International Bureau of Weights and Measures, right? The second, symbol S, is the SI unit of time. And it is defined by taking the fixed numerical value of the cesium frequency, the unperturbed ground state hyperfine transition frequency of the cesium-133 atom to be this very nice number that Miss Morgan was trying to remember of 9,192,631,770 when expressed in the unit of hertz. And this is equal to 1 second. I want to, before I go on, let me see a show of hands in the chat, please. Who, after I've read that definition, fully understands what the second is, how we define the second, or how the BIPM define the second, how it pertains to your daily life, and that I don't need to continue with the session because we've learned how we needed to learn today. Observing the chat. I know that there's a delay. Need more information? Please continue. So this is a very, very, very technical definition, right? And it is my job on a daily basis to interpret this definition, maintain the second as defined here in our time and frequency lab, and also be able to generate time, what we interact with on a daily basis from this definition. Colette Peck says it's taking a minute to settle in. All right, moving on to more specifically what the definition really means. All right. So instead of saying that, I think someone in the chat had said 1/160, it was Miss Morgan. Instead of saying that a second is 1/60th of a minute, scientists define it based on something that never changes, which is the natural behavior of a particular atom, the cesium-133 atom. I know we have some chemistry people online that can relate to the cesium isotope. So in the video, I'm not sure if we were online when a video was being shown earlier, right? When a video was showing earlier, basically giving the history of timekeeping. Historically, we might be familiar with sundials or using the rising and setting of the sun to basically define a day. So historically, this was one of the methods that was used to maintain time. We think of time, but to get the actual definition of time, we just need the occurrence or the reoccurrence of a specific event. So your heart beating, the rate of your heartbeat can be used as somewhat of a measuring quantity. I can say that if your heart beats 60 times, something is going to happen. But your heart isn't going to always beat at the exact same frequency, right? The sun rising and setting could be used to define a day, and it is still, in most cases, used to define a day. But the sun doesn't always rise and set at the exact same time every single day. The seasons change. Sometimes we have longer days, sometimes we have shorter days, right? So we need a more definite reoccurrence of a frequency, reoccurrence of a specific event to basically scale it to define time, something that isn't ever going to change, right? And scientists find that the naturally occurring cesium-133 atom, right? These atoms vibrate in a very precise way. And when they do, they change energy states. For the cesium-133, there's a very specific energy jump in its electrons called the hyperfine transition in its ground state, right? I know I'm still a talk kind of technical, still I go break it down even more, to get a solid understanding. So look, we understand there's atoms, right? And if we can pull back some of the information that we got, some of what we learned in high school chemistry or even integrated science, we can think of what we remember an atom is supposed to look like. And we remember electrons and electron level, and we remember energy states. So what we realized that, or what scientists like Mr. Novick historically realized, is that for the cesium-133 atom, when we introduce a specific energy to this atom, right? Let us say that the electrons, they have a way of changing energy state. They get excited. And when an valence electron, I'm going to use the term valence to kind of, get a more layman understanding. Electron moves its energy state to another energy state. It gives off a specific energy signature. And scientists is able to measure the wavelength of this energy signature. And they find that it produces a specific number, which is again 9,192 seconds, 631,770 cycles per second. And this seems incredibly precise. It is replicable. It will always remain this specific measurement for measuring the wavelength when the valence electron moves from one energy state to another energy state. So basically, 1 second is defined as the time it takes for exactly this nice pretty number of those cesium vibrations to happen. Folks, I'm going to check the chat. I know I've been going on for a while. If we don't remember anything from the webinar today that Terence Jones and Andrew Novick is going to be presenting, we should have a general scientific understanding of what defines the second. I'm looking for 4 comments in the comment section that is basically telling me that I have somewhat of an understanding of what is going on. Mr. Novick, if you want a chance to chime in on my definition of the second, please go ahead.
I was just going to chime in. Thanks. What I just wanted to add an additional kind of pop culture point to this. A lot of us have heard of quantum or quantum mechanics. And what you just described is really the basis of quantum mechanics. It's the idea that an atom can be in either one state or another state. And how you get that atom to go from one state to the other state is by kind of hitting it with this frequency. And so, a lot of people don't totally understand quantum, but now that you've just explained it, I think that's relevant for people to know that now they understand kind of what quantum mechanics is. It's a quantized state of an atom in either one state or another.
People close down. Man, in terms of
You can continue, Andrew. I think we just had a little.
I just saw some
Good
questions
points,
in the
yes,
chat
yes.
about cesium. A lot of
Oh, right.
Sonia,
Go
yeah,
ahead.
a couple people. A lot of atomic clocks have used different elements on the periodic table, the far left side, that's the alkali metals. And the reason is that they have one valence electron. So if people can think back to your chemistry class, you have atoms in a kind of with orbital levels of electrons. And a valence electron is there's one electron on the outside. And that kind of an atom is very stable. And it's somewhat easier to change the atomic state because you can hit it with a frequency and make that electron jump to another energy state or change from one spinning direction to another spinning direction. And so something like cesium, rubidium, hydrogen, ytterbium, strontium, they have this kind of a property. So, and cesium is also not really used for much else. So it's not inherently valuable or hard to find, because that's the last thing we would want to do is make a clock out of like a gold atom or something where we had to like acquire a bunch of gold to make an atomic clock.
Thank you. Thank you very much for chiming in there, Andrew. So, if it is that we're still having a little bit of difficulty with the definition, I did embed a video here that I think would do a far better job of explaining the definition of the second. Again, this is at the very beginning of the presentation, people, because we definitely need to have a solid understanding of what defines the second, because it is going to be applicable for us to better appreciate why maintaining the official standard time is essential for day-to-day living and for the modern society as we know it to operate in the way it should be operating. I know that there was some comments that the feedback for the video might be off, so I will be sharing a link in the chat to the video, but I think that this video does an excellent job, only 5 minutes of the presentation, in getting the mind going regarding the definition of the second and understanding what it takes to maintain and distribute time. I'm going to go right into sharing the video now.
In 1967, researchers from around the world gathered to answer a long-running scientific question. Just how long is a second? It might seem obvious at first. A second is the tick of a clock, the swing of a pendulum, the time it takes to count to 1. But how precise are those measurements? What is that length based on? And how can we scientifically define this fundamental unit of time? For most of human history, ancient civilizations measured time with unique calendars that tracked the steady march of the night sky. In fact, the second as we know it wasn't introduced until the late 1500s, when the Gregorian calendar began to spread across the globe alongside British colonialism. The Gregorian calendar defined a day as a single revolution of the Earth about its axis. Each day could be divided into 24 hours, each hour into 60 minutes, and each minute into 60 seconds. However, when it was first defined, the second was more of a mathematical idea than a useful unit of time. Measuring days and hours was sufficient for most tasks in pastoral communities. It wasn't until society became interconnected through fast-moving railways that cities needed to agree on exact timekeeping. By the 1950s, numerous global systems required every second to be perfectly accounted for, with as much precision as possible. And what could be more precise than the atomic scale? As early as 1955, researchers began to develop atomic clocks, which relied on the unchanging laws of physics to establish a new foundation for timekeeping. An atom consists of negatively charged electrons orbiting a positively charged nucleus at a consistent frequency. The laws of quantum mechanics keep these electrons in place, but if you expose an atom to an electromagnetic field, such as light or radio waves, you can slightly disturb an electron's orientation. And if you briefly tweak an electron at just the right frequency, you can create a vibration that resembles a ticking pendulum. Unlike regular pendulums that quickly lose energy, electrons can tick for centuries. To maintain consistency and make ticks easier to measure, researchers vaporize the atoms, converting them to a less interactive and volatile state. But this process doesn't slow down the atom's remarkably fast ticking. Some atoms can oscillate over 9 billion times per second, giving atomic clocks an unparalleled resolution for measuring time. And since every atom of a given elemental isotope is identical, two researchers using the same element and the same electromagnetic wave should produce perfectly consistent clocks. But before timekeeping could go fully atomic, countries had to decide which atom would work best. This was the discussion in 1967 at the 13th General Conference of the International Committee for Weights and Measures. There are 118 elements on the periodic table, each with their own unique properties. For this task, the researchers were looking for several things. The element needed to have long-lived and high-frequency electron oscillation for precise, long-term timekeeping. To easily track this oscillation, it also needed to have a reliably measurable quantum spin, meaning the orientation of the axis about which the electron rotates, as well as a simple energy level structure, meaning the active electrons are few and their state is simple to identify. Finally, it needed to be easy to vaporize. The winning atom? Cesium-133. Cesium was already a popular element for atomic clock research, and by 1968, some cesium clocks were even commercially available. All that was left was to determine how many ticks of a cesium atom were in a second. The conference used the most precise astronomical measurement of a second available at the time, beginning with the number of days in a year and dividing down. When compared to the atom's ticking rate, the results formally defined 1 second as exactly 9,192,631,770 ticks of a cesium-133 atom. Today, atomic clocks are used all over the Earth and beyond it. From radio signal transmitters to satellites for global positioning systems, these devices have been synchronized to help us maintain a globally consistent time, with precision that's second to none. Even with the help of these absurdly accurate clocks, it can be difficult to make the most of your time. We get interrupted, overwhelmed, or try to do too much all at once. So is there any way we can get better at managing our time? Check out this video to see what strategies we can learn from computers.
All right, I trust that after the video we might have somewhat of a little bit better definition of the second. How is it that we got to basically using the cesium element from the periodic table to be the definite standard for maintaining. Andrew, is there anything that you'd like to add before I move on to the definition of coordinated universal time?
Just the one question in the chat. It talked about the mechanism to excite the electron. We don't want to get into too much detail, but basically we just have to generate a frequency. So most atomic clocks at this scale use quartz crystals, which we all know and understand somewhat because we have them in our watches, our clocks, our cell phones, our radios, our televisions. So we have to generate that 9.192 gigahertz signal by multiplying up a quartz crystal to that high frequency. And then we interrogate, so like we hit the atoms with that frequency, these vaporized atoms, and then we see, did they change atomic state or not? And if they did, that means we're on the right frequency. So we just scan that frequency back and forth until we can kind of zoom in exactly and make the most atoms change state. And we try to just lock that frequency.
All right, man, am I lucky to have again the expert here, Mr. Andrew Novick, who trained me to be doing the session to answer some of these even more technical questions. So, continuing with the presentation, we have Coordinated Universal Time, or UTC. And some of us would be familiar with UTC, some of us might have just been seeing it. Sometimes when we are registering a new device, like a new phone, we might be selecting specific time zone. Locally, we might be select question to the chat. Which time zone are we in? And when you're setting up your device, which time zone are you selecting? And what is there? What is the reference that you experience? Mr. Quick, remember I did say this should be an interactive session. I want people to basically take away as much as they possibly can. So Just looking for one or two response. I see GMT -5. So Greenwich Meridian time, Meridian time -5. So again, all of these devices also haven't been maintaining or hasn't been updated to reflect coordinated universal time just yet. But coordinated GMT basically complements coordinated universal time, which is a time scale that is still operational, but the current standard is basically UTC, and each country, again, like Jamaica, should maintain their realization of coordinated universal time. When we do that here, its tagline is UTC BSJ, because BSJ maintains the time and frequency lab, which maintains the official standard time. And on a monthly and daily basis, we submit time directly to the International Bureau of Weights and Measures, which publishes the UTC report on a monthly basis. There's also the System of Inter-American Labs, which we also submit our data to on 10 minutes, every 10 minutes. We're submitting, and we also have our own time scale for the Americas. So there's the same. I'm going to be showing data from each of the time scales later on in the presentation, but just to get a general understanding again, I have here on the slide the international time scale maintained and published by the International Bureau of Weights and Measures. This is UTC, and this is a collection of the atomic clock stabilities. This is important, maintained by the various time and frequency laboratories, such as UTC CENAM in Mexico, or UTC NIST for America, and locally UTC BSJ. I've taken this source directly from Lombardi. Mr. Michael Lombardi was very instrumental in giving me an opportunity to collaborate with researchers at NIST. Unfortunately, the minute I arrived, he was retiring, and I was basically handed to Mr. Andrew Novick, who did an excellent job at training. So moving on, we want to speak also about the common view technique, right? So there's a saying to say that if we have two sources of time, how do we know which one of them is true? Technically, we actually cannot tell which one of these two sources is true without having some kind of other source to compare it, right? And this is what is called the common view technique, which is the primary technique used for time and frequency lab, like the one maintained at the BSJ, for the comparison of time scales, right? The source here is from Lopez Romero. Though he wasn't there at the time, I would have also received some training from our colleagues at CENAM in Mexico, Querétaro, Mexico. And it is Mr. Lopez Romero, who basically is foundational in developing their time and frequency laboratory. So when I was introduced to the colleagues there, I would have been familiar with Lopez Romero. He's even responsible for some of the papers that we've published. So focusing again on the common view technique. So if I'm maintaining a time and frequency laboratory in Jamaica, I cannot just be distributing what that time is local. I have to give it some representation of the geographic position. Where is it that I'm distributing this time from? And this is where GPS or any form of constellation of satellites, global navigation satellite systems come into play. The atomic clocks that we use to basically maintain the frequency, maintaining the stability to define our time, each GNSS satellite has atomic clocks on board, and they're also maintaining their local time scale. And for countries to communicate with each other, telling each other, hey, this is the time that we're maintaining here, they need to distribute that time with respect to their position, right? And if we're distributing that time with respect to our position, we use We in Jamaica use GPS. So these onboard satellites has atomic clocks, right? And there's an antenna on our roof that consistently communicates with a minimum of at least 4 to 7 satellites at any given time, consistently making a comparison of the time being maintained in Jamaica with all the other laboratories that is currently maintaining their time. This is what is called the common view technique. So where I am at, cannot just distribute my time, nor can clock B. A double difference is happening where clock A is making a consistent comparison with a common GPS satellite, and that same GPS satellite is also making a comparison with the time in clock B or at another location. And then it is through that common comparison we can have an understanding of what our time is in respect to another country's time or another country that is maintaining an official time scale. In the chat, I see I am in UTC -6 US Mountain Day. Oh, that's Andrew. Mr. Young says, how is the BSA disseminating the time locally? All right. I'm going to get further into presentation, Mr. Young. We get a better understanding of how is it that we are distributing our time. All right. So here's a brief overview of some of the key equipments that is used in our lab to maintain our time on our official standard time, which is UTC BSJ. The most basic method, remember, we are just coming on as an official laboratory maintaining time. And we've been internationally recognized by the International Bureau of Weights and Measures. But we've done this by using basically the minimum resources that we have at hand. So primarily, we use the 5071A cesium standard, and this is currently maintaining the definition of the second, right? So we have 2 of these atomic clocks. There's 1 spare in the laboratory that's running, and they create an ensemble of stability, basically. Remember, we define the second by having the reoccurrence of a specific event, right? And that event is that nice 9 billion number occurring at a specific frequency. So each 5071A standard maintains this frequency and we create an ensemble, right? But again, remember, we create the ensemble and then scale it to get the definition of 1 second or to get the local time. But we cannot just be maintaining the time where we are. We have to communicate it with respect to our position. And we do that through using the 4380A sync system, which is essentially a GPS receiver. This system in the middle creates what we call a virtual time scale, right? And then makes a consistent comparison with the signals it receives from 5 to 7 GPS satellites, always making a comparison. And it is through this system that we're able to keep that ongoing comparison with other laboratories. Mr. Young had asked, how is it that the BSJ disseminates that time that we realize using our 5071A and the comparison that we make using GPS? Primarily, we are using the S650 Network Time Protocol server, and this is a Stratum 1 level reference. We had mentioned we use the cesium from the periodic table as it is an incredibly naturally occurring, an incredibly stable frequency for the definition. There's also the rubidium element that also can be used to generate time from an atomic clock. So the S650, the Network Time Protocol, uses the rubidium element, and basically operating in the same way, we generate that Stratum 1 level time source, disseminating time over the internet. So NTP stands for Network Time Protocol, and this is basically a set of rules or instructions that govern how time is disseminated over any network, right? We also want to generate a 1 pulse per second. This is what makes the time signal actually a time signal, as well as a 50 megahertz distribution amplifier, which aids us in calibrating other devices that require or operate some kind of onboard element that is used for referencing time. So primarily we use the network time protocol server for distributing time, and it is disciplined directly to our ensemble. So this makes it a stratum level. I'm going to show a diagram on the next slide, and the next two slides, I think. This makes it a stratum level 1 source. So we have an IP address, a static IP address that our ICT department has helped us to establish. This, if you're given the opportunity later on in the presentation, you'll see how you can synchronize to the stratum level 1 source. But if you're using this source, that means that you're directly connected to the BSJ's definition of the second. There's other methods to disseminate time locally, right? But for now, we are using our primary method is using network time protocol. The National Institute of Standards and Technology, NIST, where Mr. Novick is from, has other methods of distributing time. Mr. Novick, if you would like to chime in for a second to basically share the other methods of distributing time, please do.
Sure. I don't have a slide for it, but we also distribute NTP, as do a lot of national labs. We also have some radio broadcasts. So we broadcast a time announcement over shortwave radio from Fort Collins, Colorado, not far from Boulder, where I am, and the island of Kauai in Hawaii. And the Boulder station also broadcasts a low frequency signal that clocks and watches that are manufactured to receive the radio signal can actually set themselves to the time of day using those radio signals. We also have a web clock, which maybe you'll talk about your web clock, time.gov. And that is kind of a simplistic way of disseminating time just to the 1 second resolution. Whereas NTP or the radio can deliver something on the order of microsecond or milliseconds. What other ways do we?
Yeah, that's about the primary ways that you've been using.
Yeah.
All right. For those of us that's joining directly from the BSJ, we might be familiar with that very colorful application that pops up when you log onto your computer, which is basically our secondary method of disseminating our time. But it technically is still using the same not technically, it is using the same principle. It's pinging the same S650 NTP server every 10 seconds, I believe, asking it, hey, what is the time, and displaying that time directly. Ideally, what we want to have is to turn that application into a website for the country so people can directly log on and get a direct source what the time is. All right, so just a little bit more. This is the photo on the right is the rack, the primary rack, or not entirely exactly accurate what the rack looks like in the time and frequency lab, but all the devices seen from the previous slides here is neatly positioned in a single rack to give the user the ability to basically maintain and manipulate the entire system. Right, so through the donation of a time measurement and analysis system, TMAS, that directly Mr. Novick is responsible for, NIST donated this piece of instrumentation to the BSJ's lab, among other laboratories in the Americas region. And through this system, we're able to submit timing data every 10 minutes to the SIM time scale, right? Which is globally recognized and complements coordinated universal time, right? I'm not going to go on at length with about the TMAS system when the literal expert who builds the system is online. Mr. Novick, if you have a chance to tell us about the TMAS system.
Oh, we want to talk about it now?
Sure, yeah,
Oh,
go
okay.
ahead.
I thought you were saying I was going to do it later. Yeah, so we built this system. If you remember Terrence's slide where it showed Earth and two different labs and a satellite. So this device that we made has a receiver inside, and if you plug in a clock output, so say your clock B, and we do the same thing at NIST, and clock A plugged into the same exacted device. It compares that clock you plug in to all of the satellites you have in view at the time. And if we do that same thing at NIST, or if another lab, say CINAM in Mexico, or any other lab in SIM, it records all of the satellites in view compared to the local clock and puts that in a file. And every 10 minutes, it uploads the file to a server. And then through a web interface, we can look at our clock versus another clock, or Jamaica's clock versus any other clock that are in this network. And any of the satellites that we're looking at the same time, we can make that subtraction that Terrence was talking about. So we can basically remove the GPS clock from the equation, and you get clock A to clock B. And so we have this in 26 labs all through the SIM region, North, Central, and South America, and the Caribbean. And so we can all make these real-time comparisons to each other to make sure that all of our clocks are synchronized, or if there is a problem, we can note that problem.
All right. So just as Mr. Novick was explaining, here is a screenshot taken directly from the SIM website that they maintain. And these are just some of the countries that are currently submitting time to the SIM time scale. And we can make a direct comparison here. There's a nice averaging that is done. It's a incredibly explanatory graphics. If you see here in red, I have highlighted Jamaica's time scale, and you can see Jamaica's direct comparison. And this is in nanoseconds, correct, Mr. Novick?
Yep.
So at this given instant, when I took this screenshot, we were minus 1.7 nanoseconds off from the time being maintained directly by NIST, where Mr. Novick is. We were minus 10.3 nanoseconds from what is being maintained in Mexico, minus 3.5 for NRC in Canada, and the list goes on for Panama, Brazil, and this is always going. This website is actually accessible to the general public to basically see how Jamaica is performing in relation to the other countries. Great to see the black screen and go right there. Okay, all right. So this is also this is a graph that basically shows. I did this graph sometime last year, showing how Jamaica is performing from the SIM time scale showed here, how Jamaica is performing in relation to NIST and Mexico, right? In blue, we have NIST lab, which is incredibly accurate. Though the 5071A is the standard, there's also the hydrogen MESA, which is a far more stable standard that is used. And I believe this is what primarily NISTs use to maintain their official frequency. So if you take a look at the graph in blue here, America's offset is basically non-existent, right? It's incredibly accurate. I made a mistake here in the slide. The orange is the maintenance of Mexico's official time, right? And they're an average of around 10 nanosecond off. And at the time when this graph was taken, the BSJ in green here, we were around 40 nanoseconds off from that zero line, right? So again, we use two 25071A standard, which is basically the minimum, the hydrogen maser is an incredibly far more accurate piece of device that is used to maintain time. Hopefully in the future, when we expand our lab, we will be able to further improve our time offset. It has improved. If you take a look at this graph, we did make some corrections with assistance from the manufacturers from our equipment, as well as colleagues from the International Bureau of Weights and Measures. So this graph that I'm showing now directly complements coordinated universal time. And on a monthly basis, data that is used to generate this graph is published. So Kingston, Jamaica, or the Bureau of Standard is currently being published on a monthly basis in a report that is comparing us to other laboratories, as well as generating coordinated universal time. And as you can see at the very last here, from around March to April, we have improved our offset from roughly 20 to 30 nanoseconds offset to about 10 nanoseconds offset now, which is somewhat similar to where Mexico is maintaining their time scale on the SIM time scale. Moving on. So how is the Jamaica Standard Time shared? We had briefly explained this just now with the help of Mr. Novik, also network time protocol, as well as the other methods used to distribute time. So how is it that the computer that I'm currently using, or the computer that Mr. Gale in ICT is using, the computer that Mr. Young is using, what sets the time on his computer? The phone, when we are at home in bed scrolling on Instagram and we check the time on our phone, how is it that we're sure that the time there is correct? Where is that time coming from? How does it trickle down all the way from the time and frequency lab straight to that mobile device? Manufacturing industry. The lab isn't just about disseminating time, but it's also about maintaining a specific frequency. So when there's a power plant in Old Harbor, there's a power plant in Rockford, a substation that is basically feeding to the grid, the local grid that we use to receive power, the power grid. They have a generator there that needs to operate at a specific frequency. Locally, this frequency is 50 hertz. In America, that frequency might be 60 hertz. What is it that they are using to ensure that that motor that spins up, right, to generate AC current, what is it that they are using to basically ensure that it is actually oscillating at 50 hertz? These are questions that needs answering. When you're at a bank, you're using an ATM, and you're doing a financial transaction online or else using an ATM, and you see a timestamp there. You see a timestamp on your receipt. How do you trust that this timestamp there is accurate? How do you trust that this timestamp is what it says it's supposed to be? When you do a trade in the Jamaica Stock Exchange or anywhere you are, and a new IPO is coming out, and you need to purchase X amount of shares, right? The stock price is $1.20. That is the stock price that you want to lock in your trade at, purchasing X amount of shares. But by the time the transaction is fulfilled, you find that the share has moved up to $1.22. Which one of the stock prices should your share be allocated for? And how is it that we determine this? So stock exchanges, there's high frequency trade that is operating on the stock exchanges. There's a lot of transactions that are happening in just 1 second. When I purchase that stock, and Mr. Young purchases that stock, and Larry Jones purchases that stock, how do we know who to award X amount of shares? The amount of shares isn't infinite. There's only a set amount. How do we know which transaction is supposed to be fulfilled first? Right? It is laboratories like time and frequency laboratories that maintain that official time, disseminate that official time. And in many cases, these trading venues need to have a replication of the official time there, which sometimes means maintaining an atomic clock where they are to basically be able to give you that definite resolution down to the millisecond of which thread should be facilitated first, right? So these are just some of the applications, only some of the applications of when official time is needed. In the chat, I see when Larry Jones says that he submits an assignment online at 11:59. Who says that his assignment was late when the lecturer actually sees the assignment at 12:02? Like, was his time off? So, network time protocol, I had explained this before, so I won't spend very much long on the slide, but network time protocol is the primary method that the BSJ uses to disseminate our time, right? So in the lab, we would maintain the Stratum 1 level source, which is our 5071A standards, and the network time protocol server, the S650 that I had showed before, is the Stratum 1 level source, right? And then anyone that is synchronized to that Stratum 1 would be now Stratum 2, and anyone synchronized to Stratum 2 would be Stratum 3. So by the time you receive the time on your phone or on your computer, depending on the time source that you set for your computer, you might be at Stratum level 2, you might be at Stratum level 3, and even Stratum level 4. I will now hand over to Mr. Andrew, Mr. Novick, to tell us basically why the national time, the standard time matters.
Yeah, so we all want to agree. I mean, one of the cool things about being in standards is standards means we all agree on something. So I'm happy to be part of this field where countries all around the world can agree on these definitions. And so why does it matter for us just as citizens? So in our daily activities, like getting an assignment in on time, as they mentioned, or attending a meeting, something like transportation, like when is the bus going to arrive, or like making bus schedules or train schedules, or when a plane takes off. If we all have to get to the flight on time so that the flight can leave on time. So we want to synchronize, and that's probably on the order of seconds or minutes, those kinds of things. And then home devices, synchronizing your computer clock for possible stock transactions or entertainment tickets going on sale at a certain time, or online auctions that end at a certain time. You want to be synchronized, probably to the second for those kinds of things. So say if you're competing with everyone else to get concert tickets, you want to start hitting the keys right at the correct time. And then truthful time for service. If you're providing a service, or like a television station, they're getting a feed from, say, some national or international video feed. And so they need to enter in that feed right when they enter another feed. So that means they need better than probably millisecond timing to move back and forth, or move from a commercial to back to a program or to a movie. And another thing that we've talked about the definition of a second, and so far we've just talked about time of day, or time stamping. But one other important thing for us as citizens is time interval. So that definition of a second. So imagine something like a sports, say like a running race, like a 100-meter run, or something like that, where you start the clock, and then at the end of the race, whoever comes in, you're timing when they finish. So that's not really time of day, that's a time interval. How many seconds or milliseconds or microseconds did it take? And that comes from the same definition. And so time interval could be as important as time of day for measuring something like sports or chemistry or physics. Measuring anything in science would have to do more with the time interval of some reaction happening. And as far as country infrastructure, something like telecommunications, we all depend on cell phones and computers and Wi-Fi. And so those frequencies have to be well defined. And if two different cell phone towers are not synchronized, then if you're driving from one cell tower range to the next cell tower range, it needs to hand over your signal to that other cell tower. So that needs to be synchronized in time and frequency. And so synchronizing frequency is called syntonize. So that means two things are the same frequency. So anything from like web on your phone, on your computer, SMS, text messaging, WhatsApp, all of those things are data transfer, and they need to be synchronized in time and syntonized in frequency. And Terrence mentioned the financial systems, the stock market, the time stamping. If you're going to have 100,000 transactions per second, you need to have a better resolution in the timestamps so that it shows which one happens before the next one. So you have to have a better resolution and better timing to determine those timestamps. Transportation, very important for navigation. There's synchronization and synchronization with something like traffic lights, keeping like a city's infrastructure going. One of the videos mentioned the trains, synchronizing the trains. So all those things are significant. And then security systems too. There's time stamping on a security video. There's synchronizing between traffic cameras. There's a lot of legal kind of significance to when things happen, and determining maybe solving a crime or looking at a traffic accident to see who made the error. We could go to the next slide. So some key insights. So something like a millisecond error, a thousandth of a second, can affect networks, financial transactions, data processing, causality, anomaly detection. If you want to see if there's some kind of a spoofing happening or some malicious actor is doing something to a signal, you can possibly tell by noticing the timing, a timing change that was not expected. So if you have a good enough clock, you can detect something like an anomaly or a intruder. And this resolution can be milliseconds, as it states here, microseconds, or up to nanoseconds. And so the more resolution you have, the better that you can detect things. And next slide. So for businesses and organizations, financial institutions need to have accurate timestamps for transactions, fraud detection, audit trails. So now audit trails, we're entering the realm of legal metrology now. Audit trails is basically detecting the validity of a transaction. So that in a legal metrology, there might be a question who bought the stock first, and that could go all the way to a court of law. And someone from the BSJ might need to testify to say, how their systems work. And somebody said, well, I got time from BSJ, and someone said, I got time from a lab in Australia or something like that. And so we could argue about what time things happen. So audit trails and things like legal metrology. And then telecommunications and information and communications technology. So our networks, I think data packet timing and integrity. When you send like a JPEG image through an email or a text, that's all put into the ones and zeros that we talk about and sent. Maybe those packets are sent several different routes to get to an email server that gets to the person you're sending it to, and it's put all back together. So all of those things need to be synchronized, and all the packets need to come back together. And so that data integrity is very important. So much of our lives are based on digital infrastructure, so we really need good timing. Power grids, as Terrence talked about, if you're going from one power company to another and those grids, or if there's a blackout in one and the other one needs to take over, those need to be in phase. So that's that frequency synchronization. Or else you could explode like a power line box if those power frequencies are not in phase. So that handoff during a power outage. I'm looking at the chats. I don't see anything, so moving on to the next slide.
I think Mr.
Well, there
Young.
was
Oh
there,
no,
yeah.
I didn't scroll down. Okay, sorry. Let me see. Let's see. So in telecoms, how can they measure time intervals? So basically, if say you bought a phone card, or you're getting charged per minute for a call, or some kind of connection, the telecom has to measure that time interval for the call, and most likely they are using a timestamp, so it's time A to time B. That's defining the time interval. But they need to be regulated or compared. So they should be able to prove where they get that time, so to make sure that you're getting charged accordingly. So that would be the job of a national lab, and them to report how they are doing things to national labs, or national lab can investigate. Yeah, Sonia brings up a good point for medical devices testing. That goes back to that science measurements and physics and things. So, and then bullet 2, I don't know which slide that was, which one that was from, Mr. Young.
It's relating to telecommunications and ICT, I believe.
Oh, okay. So
Yeah.
that's this one. So, yeah, so it kind of comes down to legal metrology. The provider, if there's some question about the provider, a citizen or a business might have to bring up, create an investigation, and that would go to the legal metrology, which is the national lab. So this brings up a good point too, where you really want to get time from your own country's national lab. In other words, if somebody got time from say NIST, and someone else got time from BSJ, the time from NIST is coming a lot further, and there's going to be more uncertainty, and it could be some delays or asymmetries with that time. And so if two people were arguing about what time it was, say for a transaction or telecom, the legal metrology comes from that local country's lab. So everyone should be synchronizing to that local lab. And so in America, people use NIST. In Jamaica, they use BSJ. And so that's a pretty important distinction, because you can get time. You might even be able to get time from a NIST radio signal, but that's not going to be very accurate. It's going to be much less accurate than getting time from, say, NTP on the BSJ. And so the further away you go, the more uncertainty that can add. And for legal metrology, everyone should be using the same source. Also, if you use a distant signal, it may become unavailable through some kind of signal jamming or unavailability, or if some other country turned off their NTP server, now you don't have the time. So to get it from your local country's UTC lab is very important. Everyone to getting it from the same source. And yeah, I mean, there could be a lot of legal wranglings, but if you had a problem with a telecom provider and you were getting time from Sinam in Mexico, that's not the country's legal time source. So the provider might say, well, we're getting our time from the BSJ, and you say, well, I'm getting my time from Sinam. And so they're gonna win that legal argument because they're getting time from your UTC, your realization, the Jamaican lab.
Thank you, dear Andrew. For the stakeholders listening online, I hope that you're paying extra attention there, because this is something that we've been receiving somewhat of a pushback. Why should we use the BSJ's time source when I have UTC NIST? It is good to actually have the expert at UTC NIST to tell you exactly that using your country's official reference in case for legal metrology, this is what is actually going to hold up. Should I continue the next slide?
Yep.
Mm.
So in manufacturing and industry, the something like automation processes, manufacturing, they really need to be synchronized, not necessarily with the national lab, but within their own factory. So that they say something like an assembly line or robotics can work amongst itself. But that said, it wouldn't make too much sense for them to just be generating their own time, because if one machine is different than another machine, they might as well get it from the same source. So that comes back into the local UTC lab. And also manufacturers of frequency and time equipment, or clock makers or atomic clock makers, really need to be able to have a reference to make sure and calibrate their own equipment before they send it out. And so for the assurance, and the quality systems, Mr. Lang mentioned I'm the quality manager for our division for time and frequency. And so we have to define all of our processes in our quality management system, and that's how we're able to provide services. We have to prove basically to a board of all the sim labs that our quality system is a sound way that we perform measurements. And so the way we do that is by these defined comparisons and defined processes. With security systems, something like CCTV, security cameras, is also, there's time stamping there that could come to legal metrology, access control logs, the timestamps are logged, and say even with something like video and television. And then for legal compliance, we talked about a little bit, but for evidence integrity, time stamping, it used to be something like that, 11:59, did I get my assignment in on time? Or your lease ends at 11:59 p.m. You got to make sure you've moved out by then. And that's like in those kind of contracts is per the minute. But with our digital infrastructure, I mean, we're going to seconds and milliseconds and microseconds. So we really need this more precise time for the compliance. And so I'm looking at the chat, in deriving a time of death for a forensics lab. That's an interesting point. In the United States, the coroner determines the time of death, or at least estimates the time of death. And really, he's probably using his watch or cell phone. So you want to make sure, or something like in a hospital, that they say might mention time of death. It's probably to the minute. So it's a much more coarse thing. But in a forensics lab, they might be using something like body temperature or something like that and determining time of death. So that's probably more like an estimate. But you have to have some kind of reference there, and if you watch your prime TV shows, some of those things come down to split-second things of time of death and a CCTV camera and a GPS receiver or position. All those things have to match, which is what standards are all about. All right, so I think that goes back to you, Terrence.
Thank you, Mr. Novick. Just before I continue, I saw that there was a comment from Ms. Morgan that critical important for medical devices, testing on other medical matters. For some medical labs, I think they operate a centrifuge. And this centrifuge, whenever someone donates blood, this centrifuge basically spins that blood sample, or that blood sample, and it needs to be basically spinning at a specific frequency, at a specific rate. And when it gets to this specific rate, the donated blood is basically split up. It's dispersed into different sections, basically. Because I don't think blood is donated or given as it is extracted from someone. It has to be extracted. Certain parts of the blood has to be extracted. And it's a centrifuge that is used, basically. And it's time and frequency labs that do the calibration of these centrifuges. In respect to time for reading, cultures for diagnosis, seconds matter for sure. I appreciate the comments, everyone. So just to continue, what local organization should do. So Mr. Novick just speak a lot about legal metrology. How is it that for the stakeholders listening online, how is it that you maintain your official standard time, and will it hold up in even a legal proceeding? Mr. Novick just mentioned CCT footages just now. For an example, when an accident happens somewhere and there's a traffic camera that picks up this accident somewhere, some kind of video representing or showing the occurrence of a specific event, and there's a timestamp there, there's a time lag there on that footage. This network of cameras, what is it referenced to, and can you trust it? So when that video is being played in a court proceeding, I've never been in one, and I assume that they're referencing a video. Wouldn't the person be able to say that the time that is being displayed in that video footage is, I wasn't there at that time, although that person looks like me, at that time period I was here, I was there. How do we trust that the time stamp that is in that video footage is true, right? Organizations need to ensure that they are referencing for legal metrology the official source, right, for your country. And that official source for Jamaica is the Bureau of Standards. We have a trusted time source. And we've developed, again, in collaboration with our partners from NIST, Masterclock, and Microchip, the manufacturers for equipment. We've developed a time monitoring and synchronization service that allows us to basically disseminate our time over network time protocol. So it is the responsibility of these various organizations to ensure that they're synchronized to our Stratum 1 level source. This allows for the addition, basically, of network time protocol servers, which we maintain, which are Stratum 1 level sources of reference. The BSJ has the capability to monitor your performance when you are synchronized directly to us through the time monitoring and synchronization service that we've developed. We have 4 tiers, basically, from a free NTP service all the way to a premium NTP service that is needed. And we have the capability to generate monthly reports showing and indicating the performance of this specific client or this specific stakeholder of their system that can be used as some kind of certification to say that you've been synchronized to the Bureau of Standards official time source. And this is how you've been performing, and it will be able to hold up in any form of legal proceeding to ensure that you're traceable to the officially accepted local time, and that has been internationally recognized through our participation in the generation of coordinated universal time. So we have 4 tiers. I'm going to get into each one of these tiers. The first one is the basic time synchronization service, tier 1, a foundational service providing traceable time synchronization for basic clients, right? So as is, with the assistance of our friends from our ICT department, I see Syed Gill, our ICT director, the Jamaica ICCT in the chat. He says the Jamaica ICCTV system should reference UTC BSJ for sure. Yes, so it's his department that has done the excellent job of provisioning our static IP address, which is this number here that's pulsing 66.249.155.4. You're currently able to hit this address. You're currently able to set any device that you're using to our Stratum level 1 source. So if you remember the image that I showed in some slides before with the Stratum 0 source and the Stratum level 1, the Stratum 2, if you synchronize directly to this source, you are receiving a Stratum Level 1 reference directed to the countries internationally recognized. And this is available currently for free. Anyone can use this service. Stratum 2 now, Stratum 2 now is where the BSJ provides you with a certificate, a monthly report, where you would also be giving us your reference source and we will be monitoring your performance. So this is somewhat similar to a service that is offered at NIST, somewhat similar to the time monitoring, the TMAS system. However, that system uses Common View to a great extent. This is primarily network time protocol. So we'll be monitoring the performance of each stakeholder and providing on a monthly basis how is it that they were performing over the past month. So it's authenticated and secured through NTP service, which is traceable to UTC BSJ, which is directly traceable to the international standard. Again, I'm stressing it, people. We generate a monthly report with offset statistics as well as how far off have you drifted from the locally realized time. You'll also be able to get some amount of alerts to indicate whether or not that if there's a specific threshold that you need to be operating within, we'll also be able to provide with you a flag saying that, hey, let's take a second look at your reference source that you're maintaining from your location. It's ideal for financial services, internet service providers. I do believe that internet service providers also have a Stratum 1 source where they are, but it isn't complementing the legally of the official standard time source, which is at the BSJ. So through allowing us to monitor, even if it is that you maintain where you are a Stratum 0 time source, if you have a cesium there, how do you know that it is actually complementing the country's recognized time source? Clients can receive a documented performance reporting that the time that is being maintained there meets the regulatory requirements and can hold up if in the event of any kind of auditing that's happening, right? There's also the tier 3, which is a field traceable clock service. So this would put on board basically an atomic clock there. It could be a rubidium standard. In some instances, for example, the stock exchange, some instances, network time protocol isn't enough to provide that level of resolution that is specifically needed to determine if transactions that are happening are being awarded correctly. So you might need to have an actual atomic clock on board there, and we can provide this service through using the Skywire technology that we're introducing in partnership with the manufacturers for some of our equipment, right? So this gives you an atomic clock on board, and we'd basically be through the Common View technique maintaining a consistent comparison and monitoring how is it that you're performing. And if it is that a specific stakeholder is using this specific service, they would also, to an extent, be able to serve as a Stratum 1 level source. They'd essentially be maintaining, to a great extent, their official time, but we are the ones that would basically declare that this is an official time source. The Stratum, the premium service, tier 4, allows us to combine both the Skywire technology as well as monitoring your IP address, right? So you'd be basically getting 2 reports or 1 report from the BSJ that has both information. How is it that your Stratum 0 source is performing as well as a monitoring of your network time protocol? It would be somewhat to a specific stakeholder redundant, but it is that premium level of service that on time, you'd definitely be fully legally covered. We'd provide the service in the event any one of the equipment that we provide is having any kind of issues. The BSJ would have that consistent monitoring, right? And this would most definitely be ideal for clients that require that high level of precision of time, like Jamaica Public Service, the Civil Aviation Authority, as well as the Stock Exchange. This very much sums up the initial services that the BSJ has currently to offer. We're still working on ironing out our time monitoring and synchronization system, but for the greater extent, the service is available for disseminating time to our local stakeholders. We're definitely well over the 1 hour we had initially planned for this session to last. But in general, folks, the utilization of UTC BSJ, which is the official time source for Jamaica, which is traceable to the internationally recognized time, ensures that Jamaica runs on an accurate and reliable and internationally recognized time, people, right? I have a small scenario. I did basically get into explaining it before. A bank processes transaction using unsynchronized clocks across branches. What could go wrong? I basically did answer that question before. I see a question here in the chat with Mr. Gale. How does network latency affect time being acquired from our Stratum 1 level source? All right. How does network latency affect it? So, network time protocol we're using is the primary method of disseminating our time. And of course, network latency is going to have some kind of effect, right? So what we use basically, or what we define, is there's a specific uncertainty that we should be disseminating our time with, right? So whenever it is that we are disseminating the time, we have to account for what level of uncertainty is this time offset by. So when you provide the report, you would know that it should be a give and take few milliseconds. It could be 2 or 3 milliseconds. In some cases, it could all the way up to 50 milliseconds, right? So when we distribute our time, we distribute it with some amount of uncertainty. Mr. Novik, I see your camera is on. If you'd like to chime in on that specific answer, sure.
Yeah, the way that
Yeah.
network time protocol works, as well as like a web clock, is that the overall latency is measured. So you make a timestamp at the time you request it, and then there's a timestamp at the time that the NTP server receives it, and another timestamp when the NTP server sends out the time, and then a fourth timestamp when you receive back those packets. And so now you have this complete round trip latency accounted for. And so the only thing that comes into play in the uncertainty is the asymmetry. So in other words, we know the round trip delay, and we can assume that half the round trip was the packets going out and half the round trip was the packets coming back. And that's not exactly true, but that's the best we can estimate. But that's also why we do it a lot of times. So the lower latency round trip means the lower uncertainty, because you can't be wrong by more than half of the round trip. And so the only thing that comes into play is the asymmetry. And something like PTP, which is a protocol where there's a lot of packets and requests sending both ways every second. And so that kind of characterizes the network latency. So PTP can be a little bit more accurate, but the latency comes into play, but most of it is measured and taken out.
So on the same point, to further answer Gail's question, let us say that there's a specific client that is synchronized to our Stratum 1 source, and some regulation that says that their specific business needs to ensure that they are maintaining their time to less than 50 milliseconds. And this is generally the best practice from regulations that the BSJ is working to adopt. So let us say that from their geographical standpoint, with the technology that is available, the report that we provide to them, we find that they're more than 50 milliseconds off, right? This would require this specific client to have on board their own atomic clock. Because again, Mr. Novik mentioned that the latency is accounted for in network time protocol. So they wouldn't be able to basically improve their time reference if it is that they want a measurement to be done over the public internet, which is currently how our reference IP address disseminates the time. It sits on the public internet, and anyone can access it. And if we're going to be monitoring it, we're going to need to be considering the delay over the public internet. So if there's an event where the regulation says that each trading venue needs to synchronize to less than 50 milliseconds, and geographically, they are not able to synchronize to less than 50 milliseconds, they would then need that tier 3 service or that tier 4 service that has basically an atomic clock that's disciplined to our reference at the BSJ on site that basically safeguards or mitigates against having that excess that goes beyond 50 milliseconds. Gentle folks, we are at the very end of our webinar. So just to summarize, time is an incredibly critical piece of infrastructure. I was at a seminar once and someone basically called the time monitoring a utility. Just like we need to have running water at home and we need to have power that turns on our light and powers our AC. Time is a critical piece of infrastructure. It's also a utility. And it is basically the invisible glue that's responsible for the operation of our modern society. The National Time Standards ensures consistency, and it also provides you with a level of trust. And businesses locally must actively manage time synchronization and ensure that they are receiving time from a trusted time source. In Jamaica, this trusted time source is the Time and Frequency Laboratory at the Bureau of Standards, Jamaica. Please reach out to us and find out how is it that you can get your time source directly synchronized to our locally recognized representation of the official standard. We are your trusted partner, people. Please make use of our local time source. Thank you very much for listening to our presentation. I most definitely went over, but as you can see, I'm glad I've been given the opportunity to speak passionately about the Time and Frequency Lab, the effort that it took us in re-establishing the time, the partnership with international labs like NIST and CENAM, and how is it that we maintain our official standard time, how we disseminate that time, and why it is incredibly critical that we're making use of this critical piece of infrastructure. Thank you again. Andrew, if you have anything to say before we
don't
hand
run
off.
off. Just asking the audience not to run off. So please, Andrew, if you have final comments.
Yeah, just thanks for having me. This has been great. It's always fun working with you, Terrence. And yeah, let's keep these conversations going. We love collaborating with other labs. And thanks everyone for all your questions and your attention.
All right, so thank you, gentlemen. Thank you, Andrew. Thank you, Terrence. And although Terrence did say we were at the end of the webinar, we're not quite at the end. We have shared the evaluation form and we ask you to respond to that. And for those of you who remain, let me just again reiterate my appreciation to both Terrence and Andrew for the very passionate, informed presentation that we got today. You certainly have helped us to better appreciate the tremendous importance of accurate timekeeping and the synchronized systems in supporting our modern life, national infrastructure, commerce, communication systems, and technological advancements. And as you yourself, Terrence, said, you did go over the 1 hour mark. I mean, the good thing is that, we started on time. Jamaica time is serious when the person hosting the event arrives and says, the person arrives late, 30 minutes late and says, good, me not miss nothing yet. This is the person hosting the event. And so we really want to move away from that kind of Jamaica time. We know that sometimes when people say the event starts at 10, for some people that is just the alarm clock. That's just the alarm clock. We want to move to a time when we say 10, we start at 10. So as we have said, we have responded to several questions in the chat, but do you have any more questions? Is there a question that you want to just get clarified? We have 11 minutes to midday. by the clock on my computer. 11 minutes to midday, and we will be out of here by midday. But are there any questions? I see Larry Jones saying there's great presentation. Thanks, Terence and Andrew, really informative. Presentation was not at all boring. I was fully engaged, and we hope that Larry will take time to just complete the evaluation form and to say that. So again, gentlemen, thank you for your presentation. I'm seeing no raised hands, and so I am believing that just based on the interactivity of the presentation, taking the time to respond to the questions, that we have addressed quite a few concerns. We invited a cross-section of the Jamaican public, persons from finance, persons from security companies, persons in business, persons who can utilize the services, who can understand just how important this service is. So again, we invite all of you who are here to seek to respond to the evaluation. We have shared it again in the chat. We will also email to all of you who actually attended beyond the registration. So, ladies and gentlemen, as we conclude today's webinar, we hope that this session has strengthened our understanding. Certainly, it has strengthened mine of the importance of accurate and synchronized time systems and the critical role that both of them play in our society. Today's discussion reminds us that time is far more than the numbers displayed on a clock. It's a foundational measurement that supports communication, supports commerce, transportation, research, cybersecurity, financial systems. It supports the smooth functioning of our everyday life. We also recognize the important work being undertaken through the Time and Frequency Lab here at the Bureau of Standards Jamaica. We commend Terence and Ryan White, who both serve in the lab. We commend the Bureau of Standards Jamaica for its commitment. And we encourage persons to reach out to the team for any additional support. On behalf of the Bureau of Standards Jamaica, on behalf of the Communication and Customer Service Branch, it is my pleasure to express appreciation to you, Terence, and to you, Andrew, to all the persons who worked behind the scenes, sorry, to ensure the success of today's event. Thanks to Kimo Makala, who is working behind the scenes now to ensure the smooth transmission of this event to you. To all of our team in the Communication Customer Service Branch, supported by Michelle Brown and Faith McCoy, who got on the phones and made every effort to reach out to a lot of persons. And we are very happy to see those persons who are here. We'll continue to do presentations like this. And if you are interested in us coming to your organization, to your group, to share with you, just let us know. So to all of our participants who joined us today, thank you for taking the time. We encourage you to consider to continue engaging with the BSJ and to participate in our future educational activities and awareness programs. In June, in June or July, I believe we'll have another session as we focus on rebuilding with standards and helping the hurricane recovery process. So you can begin to share the information there. Thank you for partnering with us. Today is World Metrology Day, as we say, building trust. And this is one demonstration of how you can be confident and how you can trust metrology. So please stay safe, remain productive, and remember, time matters. Let us all seek to use time well. Thank you all. Have a good afternoon. And we look forward to your support as we continue engaging with you from the Bureau of Standards Jamaica, an entity in the Ministry of Industry, Investment and Commerce, Jamaica's business ministry. Thank you all.
Thank you, Mr. Lang.
Thank you. Thank you, everyone.
Terence had put something in the chat. if you get a chance to look at it. Will the summary be shared by email or can we access the information otherwise?
The presentation, thanks for that, Daughtry. The presentation will be uploaded to the Bureau of Standards Jamaica's website and through our social media spaces. We certainly will have it on our website and certainly on our YouTube channel so that you will be able to access the information here. And of course, thanks for joining us. I know that you came to us very late yesterday afternoon. We got through to you, and we're very happy that you and Ricardo were able to join us, and we appreciate very much. And I'm sure that you will recognize how we can serve you as well. So we look forward to being in touch.
Absolutely. You're welcome.
Thank you so much.
All the
Have a great
best.
afternoon,
Bye.
guys.
You as
Bye-bye.
well. Bye-bye.
Bye, everyone.
Well done, Terence. Well done.
Thank you. Thank you. Thank you.
And I think I see Alan Michael from Antigua and Barbuda Bureau of Standards was on. So I say hello to Alan.
Oh,
Yes,
okay.
Mrs. Morgan, quite a few of our colleagues throughout CrossQ were here, and thanks to Marcia and to others who joined. So thank you. Really very informative session, Andrew and Terence.
All right. Logging off.
Let me put my voice in. Very, very, very good, Terence. Speak to
Thank
you.
you. Thank you. Thank you for the comments, Mr. Young.
Yeah, man, I really enjoyed it. And I am hoping that you guys will take this island wide and give Jamaica a wider view of what you guys are doing.
For sure. I
Yeah,
anticipate doing this
don't hide it.
presentation.
Right, don't hide it behind the curtain at all. You know?
Right.
Yeah.
Thank you. Thank you, Mr. Young.
Yeah,
Very
man.
much.
You're welcome.
All right. Goodbye, everyone. I am signing off.